The goal here today is to figure out a good way to animate the motion of a robot like a submarine or a drone in the 3D space to get a good sense for what a certain maneuver looks like. And the goal is to do this entirely native in Matlab without using any external programs or renderers. We also have two other requirements that I've set for it. It has to be fast enough that I can do this for every single simulation without wanting to without having to wait a really long time. And it also has to be a high enough quality image that I can use it for things like presentations and demonstrations without feeling like the production quality is very low. Um, so in this case, I've set up a little simulation where I have a submarine doing a set of three maneuvers. This is the Cyclone Robosub submarine at UC Davis. Um, and I can see I have this control metadata graphed on my screen here. I can see I'm doing some like different maneuvers that have different IDs here. The maneuvers have different intensities. There's some timing going on here. Um, this graph is good for debugging my controller, but not very useful for telling what the vehicle is doing. The other telemetry I have here is the position of the vehicle. I can see that the X, Y, and Z coordinates of the inertial frames have this kind of wandering pattern here. They don't get very far, only about half a meter in either direction. And then the Euler angles are a complete mess. So this is why we're kind of motivated to come up with a better way to illustrate these vehicles. The problem is it's really hard to tell based on the Euler angles, or even worse, the quaternion, what the vehicle is doing. I can kind of see here that it's doing a roll first because the roll axis is going up to pi, then wrapping back around. Then it seems to be doing some kind of pitching action. Then it seems doing some kind of yaw action right here. So it looks like a set of rolls, but I would like to do a better job than this graph to illustrate that. We can also plot the thruster commands, but those are also not very helpful for telling us what the vehicle is doing, unless we happen to know how the thruster layout for this vehicle is configured. All right, so what I want is something like this. I want to be able to take the simulation that I have, and I want to run it, and I want it to pop the GIF out right away. So in this case, I'm running a 30-second simulation of our vehicle, and it includes buoyancy, gravity, drag, and the thruster forces. And this is just a set of feed-forward maneuvers with pre-scheduled thruster forces. So I have this controller that's programmed in Simulink that does all this. But for now, let's just go ahead and plot it. So what I have here is the results all get saved to this structure called results, and then I pass it into a function that calls save all outputs, and that's the thing that actually generates the GIF. I'll show the code for that in a minute. So let's run this. It'll take us about 30 seconds to execute here. We can see it is giving us a percentage of how far it's along in creating the GIF. And it's pretty fast. You can also create videos this way too at about the same speed. All right, so it's finished. And it automatically opens the folder for me because I set up my tool to do that. And if I go in here, I see I have a single GIF with the file name being the time and date I ran it at. And if I open this up, I see I have a very nice GIF of my robot doing its maneuvers. First it does that roll, then it does that pitch, and then it does this kind of flat spin yaw. And I can see by the moving axes and kind of the motion of the robot a lot better what it's doing and whether this maneuver is acceptable compared to the raw graphs. It's also really, really good for teaching beginners to this stuff what these various motions look like and how the vehicle moves. All right, so how did we get this? First of all, you'll notice there is actual like lighting and stuff like that. It's not just like a wireframe. And the mesh is much more complicated than something we could manually build up with just using the patch tool by hand. So this is actually a mesh made directly from an STL file, and I'll show how to do that in this video as well. And we can see the result is much, much better than what you could come up with making this mesh by hand like a lot of people will try to do. All right. So let's go into Matlab here and we'll see how this gets done. First thing I'm going to do is go into my function save all outputs and see what's going on here. So this function is a function that simply saves every single thing in the results structure into a folder, and it makes the title of the folder just the date and time the simulation was run in. It also has an optional input argument to make the GIF. So to make the GIF successfully, you need a couple things. You need the geometry of the robot, and you need a time series for the position of the robot, and a time series for the orientation of the robot. So we can see what this save all functions or save all outputs function does is while it's saving the data, it just grabs the inertial position and the rotation matrix from the data set for the GIF tool. And then down here, it just passes it into this save state GIF function where all the important stuff happens. So let's go see what's going on in there. All right, let me make this a little more room. So like it says, this function is to create an animated GIF and save it into file. By default, it will take about 1 second of rendering per 1 second of simulation, which I think meets my personal criteria for speed. And you can change that by adjusting the settings like the frame rate and the lighting. The GIF I showed earlier was 30 FPS. I don't want to go below that because it starts to look a little bit choppy, and I also don't want to compromise on the lighting. So that's why I have to settle for 1 second of render time per 1 second of sim time. If you don't care about the production value of these GIFs though, you can really crank this speed up if you're just trying to use it for like debugging or something like that. So what it needs is the time vector, the inertial position vector, and the vector of rotation matrices. You could also use quaternions or Euler angles here and just convert later. It also needs a file path for where the data gets saved and a name for the file. So if you're doing any kind of simulation, you should have this T position and orientation already spat out as outputs of the simulation. I'm not going to talk about how to get that here. Really, any sensible dynamic simulation will have these as outputs. And you just have to find a way to unpack these and pass them into this function, and that's all it needs. So if we scroll down here, we can see I've set up a lot of optional keyword arguments. These are completely optional, but one thing you can do with these is control the speed it takes to render by cranking down the quality. So margin controls how close the camera is to Mandy and how much white space there's around the outside. View controls the view angle. I can put 2 for a top view or 3 for that isometric view I showed earlier. Dynamic camera motion is pretty nice if the vehicle is going to be moving around a lot in 3D space. It basically causes the camera to track the center of the vehicle. It also adds about maybe a 25% increase in rendering time, so that's one you can remove if you care about speed. Some flags to make the GIF and to make the video, and then a flag to open the folder where it gets saved, so you don't have to go digging on your file system for it. All right, so just unpack all those variables if the user passes them in. So getting into the actual layout of the function, the first thing I want to do is to make the matrix positions 3 by n. So basically a short and wide matrix. So I already have a function that makes it a tall skinny matrix that's used for a lot of my other functions. So I just call that and then take the transpose of that to get my short and wide matrix. So if I'm trying to get the dynamic camera motion, what I want to do is I want to pre-generate what the bounds of the frame should be for every single frame of the animation from my data set, because I don't want to have to recompute that inside the for loop for the frames, because the more stuff I can pre-compute with matrix math, the more efficient my code will be. So I define this bound matrix. This is just the lower bound and upper bound in the x, y, and z. And you can see what I've done here is I've applied this margin to basically every single coordinate in the position matrix in the x, y, and z. So that will mean the camera is always perfectly centered on the position of the robot. Moving right along, this code just brings in some file paths. If you don't already, I suggest having some code that makes it so you can set up the same code on all different computers without having to manually change a bunch of file paths. And then we need to set up the figure. So the first thing we do is create the figure here. I make it invisible because I don't want it to actually show up when it's creating the figure. I just want the GIF. Um, and we can define the size of the figure here. This size is fairly large. Another way you can speed this code up a lot is by dropping this size down. But again, I didn't want to compromise too much on how good it looked, so I didn't do that. We also have this axis object set up. I don't know how that got up there. Um, with the parent of the figure. We're going to use this to manipulate the axes. First, we set the axes to manual mode. We don't want it to waste time trying to automatically rescale the graph. And then we're also going to set the axes as the margin around the vehicle. So this means the vehicle starts at, the graph, I should say, starts centered at 0, 0, 0 with a boundary of the margin, and then it will start tracking the vehicle's position. You could also start this as the initial position of the vehicle if you wanted to, but for me, my vehicle starts near the origin all the time, so this is acceptable. We set the view to whatever the user passed in, and then we call hold on and define our axes labels and title. Our vehicle uses a forward, right, down coordinate frame, and the inertial frame uses northeast down. So to make this look correct, I inverted my z and y direction. So it's still a right-handed coordinate system, but the positive direction points where I want it. All right. Now here's where I get all the nice geometry from. I just load this object called manipatch.mat. This is a patch structure, and I'll show how to make this from a CAD folder or a CAD file in a minute. But this is the really important part here. What we're going to be basically doing is transforming all the vertices in this patch repeatedly in a fast vectorized way without having to do a lot of work to calculate it. I also want lighting. If you don't want lighting, you can take it off and the GIF will be faster. However, it will also look bad. And we also need to figure out what the time step in the data is. I have my data set up to save at a 30 hertz interval for my simulation. But if you have your simulation set up to save at a much higher rate, I would suggest down selecting that so you're not trying to render at a super, super high frame rate. If I make my time step 0.003, that's called DT data in my code. That's going to give me 1/30th of a 1/30th of a second per frame. So the question is, okay, do I want to lower my simulation resolution to do that? You don't have to. You can have the simulation speed actually be much higher than the data collection speed. And if you're using signal logging or to workspace blocks, you can just control the rate that block will sample from the simulation. All right, so we have data at the right frequency. We get this time step from the data, and then we need to set up the transpose object. We're going to use an HG transform for this. Basically, this lets us transform the coordinates of the patch object and from the CAD a lot faster without having to manually compute the location of all the points every time step. This frame skip stuff is if you want to start passing in data at a higher rate than 1/30th of a second, and then down selecting whichever one of those frames you actually want to plot. Like if you passed in a 100 hertz data set and wanted to plot it at, say, 33 hertz, you would just skip 3 frames or skip and plot every third frame. We need to define the number of frames. This is just pre-allocating some matrices here. And then I like the percentage printout, so I have that as well. This first loop is where all the math happens. We loop through every frame we're trying to plot, and we pull the rotation matrix and the position vector out of our data that was passed into this function. We then need to build the transform matrix for H2 transform. And we can do that just by setting this set of elements equal to the rotation matrix, and this set of elements equal to the position vector. And then we save that as the matrix parameter in the transform object. What we do now is we draw the frame. And what this does is it calls it, well, there's draw now, first of all. Draw now is just drawing the patch again. But what we did is we changed where the patch gets drawn by updating this t object parameter. So there's not actually any plot calls in here. I just have my patch defined previously, and then I call draw now right here to render it. The limit rate parameter, just to help it be faster, it doesn't really make too much of a difference for the kind of FPS I'm running. All right, now what we do is we just capture a picture of that frame using getFrame and save it to this array. And we also increment this index right here. This index is handy if we're doing data printouts. We don't want to print every single index because that would be a lot of print statements. We'll just do it every, say, 10 frames. If we do dynamic camera motion, we can update the axes parameter here just by passing in that bound matrix we defined earlier, specifically the element that corresponds with this time step k. For the print statement, this little block of code here is just to check if the frame index is a multiple of 10. So every 10 frames this triggers. I then define the percent complete, and then I print it to the command window. This code right here basically causes my next print to overwrite the previous print by basically calling the backspace character on it a bunch of times. And that's kind of nice because it means I don't have a long scrolling wall of text. I just have the single parameter for percentage updating repeatedly. And then we close the figure. So all our frames are now stored in this frame array, and I can call them with various other functions. There's two ways to do this. You can make a video or you can make a GIF. I like the GIF better, but there are reasons you'd want the video as well. All we need to do is create a video writer object and write the video to the specific file path we define. For a GIF, it's a little more complicated, but the same kind of deal. We have our GIF file path, and then we loop through all the frames. You don't have to. You can have this be an RGB, but I compute all the frames to grayscale for speed. This is about a 5 times increase in rendering speed when you do this, so I would highly recommend this step. Usually grayscale is plenty. If you really want color images, you can do that. Just you'll have to be more patient. And then we convert that gray frame to a indexed image A with the color map given by map. This 256 here is the size of the image. It's 256 by 256. You can lower that too, but in my experience, it only adds like half a second to performance, so it's not the big deal. And then I call image write to basically append each frame to the GIF pretty simply. So that's it. That's the entire set of code there. We just do some more printing of the telemetry to the user, and then we open up the folder. I've only got this working on Windows so far because I'm using WinOpen. I was trying to use Open, but that wasn't quite working, so I haven't figured out how to make this work on Linux or Mac yet. I mean, the whole renderer works, just not the open folder parameter. All right. So the real bottleneck here is in this operation up here in this loop. The big bottleneck is in the draw now function call. Everything else is quite quick, like less than a second, even for large data sets. The main things we can do to improve this are by decreasing the work Matlab has to do each time it draws this frame. So we can do things like removing features from our graph like the axes. We can do things like taking away the lighting. We can do things like decrease the frame rate. And each of these does have a pretty considerable increase in my plot time. The main issue is, though, that it makes it look bad, which is unacceptable to me. So that is the entire code. Once I get this all cleaned up, I'll link the GitHub repository to it. And the only other thing to talk about here is the input parsing or not the input parsing, the patch parsing from the CAD. So I'll go into my scripts folder for this project, and I'll show you what that looks like. Let's see here. So I need my CAD imports folder. So what I've got in this CAD imports folder, I can't make this much bigger. I've got an STL file that is the simplified model of Manny the submarine. That's the thing you saw in the GIF. Um, and I basically just exported this from my team's CAD folders. If you're modeling a vehicle, you can make the CAD as elaborate or as simple as you want. Simple vehicles tend to render faster because they have less complicated geometry, so fewer lighting calculations, fewer patches. And I have this script called setup mani patch. So this script takes a couple seconds to run, but you don't have to run it every time. You can just pre-compute all this data once and then save it to the mani patch object, because this is basically just defining the vehicle's position in the vehicle's local frame, and then it will just rotate and translate those coordinates later. So the way we do this is, oh, some of this stuff is actually left over from when I used to actually be running the whole code in here. I'll show you the stuff we actually need. Let's see. All we really need is this function call right here. Model equals STL read, and then I have the file path to my STL file. So what this does is it creates a model object, and that model object has a set of points, which are the vertices, and a set of faces, which are the connectivity lists for the patch object. Um, Now, my particular CAD model is in inches. So the very first thing I do is I define a scale factor to convert my units to meters. The other thing I do is I want to make sure the origin of my model is about where the origin of my body frame is supposed to be. So I can just add this little offset as well to shift the vehicle around to where I want it. Um, and then all I have to do is once I've offset the model, I will also scale the model by this scale factor to convert it to the correct units for my scene. So the parameters I care about from here are points, and then I do some manipulations on points, and connectivity list, which tells Patch where to draw patches in between. Now, by default, when I run this, I have something like 14,000 triangles in my model, which is way, way more than I actually need to get a good sense of the shape. So I call this function called reduce patch, and I reduce the number of triangles to 10% of the original value. You can crank this number as low as you want, and it will increase the rendering speed, or decrease the rendering speed if it's larger. I said that backward. The only problem is if you make this number too small, your vehicle starts to look kind of chunky, and I like those nice smooth contours. So reduce patch is the function there. And then what I do is I call this rotation matrix right here. In my CAD, my vehicle is not aligned with the forward, right, down frame I want to use. So I just define this little rotation matrix to flip it to where I want it. And then we define our patch object. So there's a lot going on here, but the important parts is we have our faces defined, we have our vertices defined, and we have this color string, which gives us that nice gray face color. And I also made my faces solid, which I think looks better. Um, and I turned off the line style. The lines get really, really messy because they'll try to draw every single triangle, which not only is slow, but also looks terrible because the triangles aren't like a nice wireframe. They're just like a whole bunch of triangles bladder all over the place. And I also need to define lighting. This step's optional, but it looks pretty bad without lighting. These next couple sets of calls here are just setting more parameters of the patch. I like lighting, but I just want the flat lighting scheme, which is the fastest. I don't need any edge lighting or backlighting. And this stuff right here is just the code to set up the plot, which we don't actually need to import the file. So really all we need is this block right here where we get the patch right here. And then what I can do is I can just save this patch as a variable to the workspace. I can do that by just running this code once and then going over here to my workspace. See if I can grab that. And if you didn't know, you can right click on one of these variables and you can save selection and you can save it to your workspace. In this case, I saved it right here as manipatch.mat. And then you don't have to run this code ever again. You can just have that manipatch be called by your state saver without needing to worry about that anymore. If you update your cat as well, this is also pretty easy because you can just update this STL file path and regenerate this mesh whenever you want. So the result of all this is these nice, very high quality GIFs where we have the vehicle translating and rotating. And it's quite quick to make them as well. Yeah, I think that's about it.